phenomenon could be responsible because we have a multi-scale process. We think that it could be responsible for large erosion events we observe in the mountain stream, for instance, when the bed aggregates for a long period, with this armoring stabilizing the bed and allowing a steep slopes with a large amount of sediment deposited below this armor. But when the layer of this is removed by even a little flood, because here we don't need a large flood for this to move, you can have a large degradation and this kind of incident. So here is observer. So we have a scale problem because, as I said, we suppose that it could be what is observed in the field, but we know that, for instance, in this experiment, we need 15 hours to build the pavement and 15 minutes to destroy the bed. So it means that in the field, how long will you need? 10, 50 years to build a bed and maybe one flood just to flush it away. Next situation, we go far downstream, and this time we consider that the vertical distance is small compared to the downstream Wyoming, actually. For instance, here is a gravel of the Bar River, the Art River in France. And if you see the different grain size distribution, you have here 14 millimeter, 48, 60. So the coarse fraction is here. The armoring is very present here. So we can explain that, many people have explained that by the different transport to the different sites by the flow. If you have, for instance, the coarse element where by inertia deposit on the head bar head, the mixture can be transported by the channel, and the finest element can deposit by the secondary flows in the bar tail. So here the armoring process is very evident. What happens in the middle of the channel? This is a question. Can we observe in this channel what we observed previously in our flumes and in the constrained streams? But the difference, maybe compared to the previous experiment, is that this time the channel can also evolve in width in the plan, not only in vertical. So we did some experiments with my previous students. We used as a reference the LIVES experiment of 91, and we observed stabilization by armoring of a 10-hour experiment. We did a 100-hour experiment, and what she observed is Pauline Leduc was actually fluctuation of the bed between these two states, with here a near blind bed and here externalization, lead to the destruction of the local pavement. This is a fluctuation of the slope and the width of this experiment and the solid discharge. So I can use it. Sorry. Oh. Okay, so this was explained by her observation, by actually generalization of the armoring process at the bar head with time, which take more and more place and can generalize the armoring over the entire bed evolution. But this is once again, and this is also associated with the local slope variation of the bar head and the peripheral pole system. Once again, we have a scale problem because in the field, we must consider century length time for scale bar development, according to Church. So, it's an interesting exercise to see what happened in the flume, but in the field, it's another story. What happened in braiding rivers, we tried an experiment with 400-hour experiment. We did not observe really a fluctuation of the wall channel like in the previous experiment, but in each of the branches we observed this kind of armoring, construction and destruction. More generally, in terms of channel evolution, it was more in the plan due to actually the effect we observed in this situation. When you have a local degradation of your channel, you will not have only a vertical variation, but more a deposition and a lateral variation.
You finish in about 2 minutes?
Yeah. So this means that we will never observe in this kind of situation very large slope fluctuation, but rather lateral variation of your channel. Okay. The last situation is when the vertical distance can be negligible compared to the longitudinal length. And it concerns two extreme situations. Actually, it's full mobility or when the coarse fraction is not mobile at all, and you cannot have this trapping effect, and it's more maybe the pavement, the situation with pavement. Okay, conclusion. Armoring is a complex process. Hydraulics alone cannot explain armoring, because we have seen that we have a total destruction of the bed without any change in the discharge, actually. The armoring is not only a consequence transport, but is also a powerful driving process, controlling bed load and the morphology. And it's difficult to conclude that the armoring is due to one or another process. Actually, maybe all these processes could participate to a general dynamic equilibrium of the system. Okay, and we have a big scale problem, and we need to trust the fluid. I don't know how, in which extent, but we need to trust the fluid. Okay, thank you very much.
Okay, we have time for questions. Maybe we'll get the lights on so I can see people and turn them off as needed.
Okay, I can do it like this. I was wondering, do you have some idea about the LV and LH lengths for different slopes?
Not for different slopes, because for given shear stress range, for different shear stress, we have the fluid measurement. Actually, how we measure this distance was your question. If you inject a sediment mixture in the flow, you will have this trapping efficiency, which will decrease in the downstream direction. It's really an upstream phenomenon. And you can measure clearly an extent of a thickness concerned by the trapping. And over this distance, you will change the process. This is the compartment model I presented. You will have different process downstream of this distance, which can clearly be measured in the film either by the morphology, surface morphology, or also by sampling the subsurface material. But we have, in the film, it can be 1 to 3 meters long. I don't know in the field, I don't have any idea.
So if, let's say we have some armor layers in the Dutch Rhine, how thick should it be? That's like a question which is interesting.
Absolutely no idea. But if you want to, actually if you want to relate that what could be in the field, for instance, you can imagine in the field, the armor is destroyed locally. Fine sediment are released. What is the distance over which we see these sediments before they disappear again below the surface? This is typically this kind of distance.
So I'm still a little bit confused. Is LV the distance, sort of a thickness of that layer beneath the surface, or a distance, or? It's
this vertical distance during the trapping mechanism.
Okay. So it reminds me a little bit of Philippe's results.
Yeah, sure.
Right. So do you? I'm wondering if there can be a comparison done. I mean, it seemed like his was partly grain size dependent, and I'm just wondering if there's if you've tried to make a comparison like that, if there's some grain dependence, or is it a combination of conditions and grain size dependence that you thought about what controls that?
If we go back to the history of this film experiment, 20 years ago, which I was not there, the idea originally was to develop these two kinds of experiments in the same lab and to compare, to have this feedback, but we never did that work. So we should, you're right, it's a question we still need to analyze here. Because of course the two mechanisms are related, it's quite similar, but I'm not sure that, but even in the literature I don't have any information about this kind of processes in flume in water case of bed transport.
Okay, so another question, but it's almost the same question in some sense, is that you alluded to, and you said, maybe there's some granular physics to explain this. Did you have anything more particular in mind? I can't remember which slide. You sort of said, well, maybe the granular physics can explain this. But I didn't.
What, sorry?
Do you at some point, you just toward the end, you said, well, maybe this is something where granular physics can help explain this. And do you have any ideas as to, I mean, what do you have in mind? Is the sorting process or the sort of beyond?
Actually, what we know, we don't know many things about all this process. All comes from people from the granular physics, people who worked on the process industry. Only these people, they know very well all these processes of sorting, and this is what you presented this morning with different experiments specifically designed for this kind of. But in terms of people who work on hydraulics and silicon transport, I did not find any information, and I'm not sure that we did yet the effort to see exactly what has been done in the different disciplines. So I'm convinced, and this is also what your talk and Philip saw this morning, that we need to investigate more of this.
Maybe if I could touch bases more in detail.
In the experiments we did in Tsukuba, where we had migrating Bembo sheets, I was just looking, because I didn't think about the slope variation. We did have some slope oscillations. But the thing I was later impressed with is that we could apply Gary's service-based transport model and accurately, with no adjustment knobs, predict the progressive service change as we reduce the supply. And to me, it suggests there is a persistence of a dynamic armor layer, if you will, that isn't. I don't know if you mean to suggest it, but you gave me the impression that I should be thinking of armor layers as building up, stabilizing, and then being wiped out. And yet, I think what Gary's service-based transport model does is it says it can be there actively exchanging, and it's an adjustment to relative supply. I think we've run this on 2 different sets of flume experiments without any calibration. It does predict persistent grain size change. So what I'm leading to is wondering whether some of the dynamics you get in your model is a consequence of having just 2 grain sizes. That there's, it's antagonism, as you put it, because you can only be in 2 states. And so I wonder whether some of the, I think many things you've shown are really quite interesting and quite valuable, but I wonder whether part of the drama there is the 2-particle influence on the behavior of your system. Do you think that's the case?
Actually, we did the same experiment with unimodal Siemens, and we observed the same process. Less emissions, but
same process being that the whole system armored up
exactly the same.
and destabilized?
Exactly the same. It's not a question of bimodal or unimodal. We did all tests with wall roughness, without wall roughness, because we had all this question, we tested all configuration, we always obtain this kind of configuration. But the difference maybe here is what I'm presenting this morning is a kind of experiment with essentially steep slopes. So the middle slope was 1.5%, and the shear stress was such that the coarse sediment was always mobile. I'm not sure that all experiments were in these situations. We did some experiments on steep slopes by setting the shear stress below the critical shear stress for the blue sediment. So we did a specific experiment for that, and we did not observe this fluctuation. In that case, we observed normal construction, armor or pavement, I don't know how you got that, with efficient transfer downstream of the sediment, exactly like Joel presented yesterday, by local segment of the structures. So you have progressive transfer downstream, but absolutely not this kind of trapping and bed destruction.
Yeah, I have to think about it. So we had we've had our experiments for many hours, and statistically the bed it didn't go through wide pulses. It did have slope variations, but it didn't form in.
I cannot answer you exactly to your question. Actually, what is sure, the steeper the slope, the faster is the phenomenon. This is why we work on steep slope. I tried some experiments below 1%. It's very, very, very low. So, if you did some experiments from 9, 3, 5, 3, 1%, I observed all the same fluctuations until 1%, and at 1% I gave up because it was so long that I'm not sure that if we carry on this experiment very long, if we can observe this kind. I don't know. I don't have the answer, and I will not tell you this is what we observe. I just have some observations made on the steep slope. But I don't have, this is something I would like to do, because I know very well your experiments too. I'd like to see what happens if we test this experiment on a very long term, how it evolves.
Last question.
Sorry, I just wanted to clarify that I understand that correct. So does that mean if you have less than 1% slope, then the arm ring doesn't get destructed? Or it doesn't?
If I have what?
If you have less than 1% slope?
No. What I mean is that
What it means is if he has less than 1%, he's not patient to wait long enough to see.
Yeah, but in principle, so let's say you wait in infinity, you suspect there might be a point at which it no longer gets destructed, so it kind of gets fed as
for
fast
me,
as
there is no reason why the processes would disappear for milder slope, because you still have the mobility of the sediments, so the interaction is there, it should be maintained. But the process is very long, because the transport rates are low, and the distances concerned are longer, and it's very long. If you want to observe something, you need to wait a long time. When I did first this experiment I showed you with the different movies, I waited 10, 15 hours. I was a PhD at that time, very, very happy to do my experiment. I learned at school that you have this balance. You put constant discharge and discharge, you obtain a slope, and you are happy. I opened this slope, and boom! After 15 hours, I wanted to suicide, because I was sure that something was wrong in my experiment. I was sure that I touched something. So I start again. After 15 hours, boom! Okay. So it started like this, like by an accident. And we have been performing this kind of experiment for 10 years now with different PhD students, with different conditions. We always observe the same process. But we don't know what happened for minor slope. I showed you a short experiment with a bar destruction. This was done by my PhD student. I did not do this experiment, but it was a preliminary experiment, very simple. I'm not sure that we can reproduce that with a complex mixture. This is something we should do, but we need a long experiment, I think, to see what could be expected.
I guess we have time for one more. You had your chance, Kimberly.
Sorry, Kimberly, my question is going to probably be a lot more basic than this. But I'm just curious if you think this has some relevance to check dams in torrent systems. I mean, I know you think about check dams.
Yeah. Actually, my PhD working on check dams now, I've done some experiments with this kind of material, with and without check dams. And what he showed actually is that this kind of bed control, the control of the bed by the armor, can be reduced by the presence of check dams. And because if you put check dams, this kind of compartmentation I showed in the conceptual model are materialized by the check dams in the field, and you disconnect the different parts of the structures of the field. And actually, with check dam, you will have very often many pulse of sediments going out the system.